Welcome all. Let us continue our discussion for the subject discrete mathematics meant for semester 3 second year students. We are into unit 1 and today we'll be discussing about propositions, predicates and quantifiers. We are referring this prescribed textbook called as Discrete Mathematics and its Applications, 7th edition by Kenneth H. Rosen. Let us verify this in the syllabus prescribed books also. You can see this. Currently we are using Kenneth H. Rosen's book for this topic. So our topic of discussion for today is application of propositional logic. So as mentioned here, logic has many applications in computer science and other domains. So when I am applying mathematics to represent natural languages, okay? So natural languages statements are imprecise or ambiguous. This ambiguity can be removed with the help of these statements, okay? So these statements are what? These statements are languages of logic. Logic can be used for many purposes as mentioned. It can be used for specification of software and hardware. Propositional logic and its rules can be used to design computer circuits, to construct computer programs, to verify the correctness of the programs, and to build expert systems. So let us look at propositional equivalences. Let us say there is a compound statement and that compound statement is true. Okay. So whatever may be the truth value of those variables inside, then such a proposition is called as a tautology. If the compound proposition is always false, then it is called as a contradiction. If a compound proposition is neither a tautology nor a contradiction, then it is called as a contingency. Let us take these propositional variables, P or not P. To make it simpler, let us say P is 1, true, and not P is 0. So, true or false, 1 or 0. So, the result of this 1 or 0, true or false, or P or not P, is always true. Such case is called as a tautology. Such case is called as a tautology. Let us take the next case, P and not P. So we'll replace it with ones and zeros. So 1 and not 1. So 1 and not 1 is 1 and 0. So 1 and 0 is always false. Then it is called as a contradiction. Okay. So let us look at the De Morgan's law here. Suppose we have like this, not being applied to P or Q, then the resultant will be not of P and not of Q. Or if not being applied to P and Q, then the result will be not of P or not of Q. So this is first law, this is second law of De Morgan's theorem. There is a small exercise here. We have to prove that these two compound statements are logically equivalent. So first one is what? Not of P or Q. And the second one is what? Not of P and not of Q. So what is there? How many variables are there? There are two variables, P and Q. So how many possibilities are there then? 4 possibilities. 0, 0, 0, 1, 1, 0, 1, 1. That is false, 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 true, true, false, true, true. So first let us calculate P or Q. When I say R, what it indicates? It is inclusive of. So any one of them should be true for the output to be true. So let us look at P or Q output. T or T, both of them are true, so the output is true. T or false, one of them is true, so output is true. F or T, true. F or F, false. So this is the resultant for P or Q. So not of P or Q can be calculated by just replacing the true with false, false with true. So the resultant will be false, 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 true. Similarly, from this statement, we have to calculate not of P and not of Q. So not of P will be false, false, true, true, and not of Q will be false, true, false, true. So now we have to take the conjunction of not of P and not of Q. So the not of P and not of Q will be false, 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 true. So if you look at this, not of P or Q has values false, 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 true, and not of P and not of Q is having value false, 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 true. So both of them are logically equivalent. Hence we proved that this not of P or Q and not of P and not of Q are equivalent. So similarly, you can try a small exercise that P implies Q and not of P or Q are logically equivalent. Now in this next table, you can see that we are having three variables called as P, Q, R. As there are three variables, 2 to the power of 3. Okay. So how many possibilities are there? 1, 2, 3, 4, 5, 6, 7, 8 possibilities. So as there are three variables 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So same thing what we have to calculate is to prove this that they are logically equivalent. We'll first calculate Q and R. So this is Q and R. So when I perform AND operation, both of them should be true for the result to be true. So let us take Q and R, true, true, that's it. Similarly, we have P or Q needs to be found out, P or R needs to be found out. Then we need to find out P or Q and P or R. So this is the resultant, and we need to check if they are logically equivalent or not. So you can check that this P or Q and R as well, this P or Q and P or R are logically equivalent. So you can try one more exercise, this one. P or Q and R and P or Q and P or R are logically equivalent. So let us look at few laws. This is the identity law. You can see here there is a variable and an AND operation is being performed on this variable with a truth value. So whatever may be the value, whatever may be the value here, as in P, if the P value holds true, then the resultant is P. If the P value holds true, then the resultant is P. So this is identity laws. And you can see here domination law here. So you combine a truth value with any variable, with an OR operation, the output will always be true. You combine a false value with any value of the variable and perform an AND operation, the result will be false. This is the domination laws. So next law is idempotent law. So that is P or P will be P, P and P will be P. If you take this double negation law, it will be not of P will be P. If you look at commutative laws, so P or Q implies Q or P. So even if the order is changed, nothing will happen. Similarly, P and Q will be equivalent to Q and P. Even if the order is changed, the output will be same. Let us look at the associative law. Here also, I have changed the order, but the output is same. Distributive laws. So when I am applying the distributive laws, so P or Q and R will, the resultant will be P or Q and P or R. P and Q or R will be P and Q or P and R. We already seen the De Morgan's law. Let us look at the absorption law and negation law. So absorption law will be P or Q will be equivalent to, P and Q will be equivalent to P. Because then P and P or Q will be equivalent to P. So similarly, negation law will be P or not of P will be true. P and not of P will be false. So there is a small exercise mentioned here. You have to show that this logical statement is a tautology. For that, we are taking the exercise problem question. P or Q implies P and Q implies P or Q. So it is like A implies B. How I can represent A implies B? implies P can be represented as not A or B. So this is not P and Q or P or Q. Now, when applying the De Morgan's law, this will be simplified as not P or not Q. Okay. Then using associative and commutative laws, this resultant will be not P or P or not Q or Q. So if you look at not P or P, it's a truth value. If you look at not Q or Q, it's a truth value. So the OR operation is performed. So the output is a truth value. So hence it is a tautology. Let us look at predicates and quantifiers. Let us look at predicates and quantifiers. Say for example, I have a statement that x is greater than 3. Here x is the subject, while greater than 3 is the predicate. Here when I say greater than 3, it is the predicate. What is the predicate here? It is the property of the x. It is the property of x. That can be represented as P of x. Here P denotes the predicate, that is greater than 3, and x is our variable. Now, if this statement holds, okay, P of x for x greater than 3, what will be the truth values for P of 4 and P of 2? So here the truth value of P of 4 will be true and the truth value of P of 2 will be false. Let us look at, after predicates, let us look at the quantifiers. Okay, quantifiers mention the extent to which a predicate is true. Okay, so you have something called as a universal quantification, which indicates that the predicate is true for every element. The predicate is true for every element. Now we'll be using this symbol like this for all x P of x, which indicates the universal quantification. It can also be referred as for every x P of x. Here this first quantifier is the universal quantifier by name for all x P of x. So which indicates P of x is true for every x. This symbol is for existential quantifier. This symbol is for existential quantifier. There exists x P of x. So there is an x for which P of x is true. Now let us look at the De Morgan's law applied to the quantifiers. Suppose I have like this. Not there exists x P of x, I can represent it as for all x not of P of x. If you have not of for all x P of x, that can be represented as there exists not of P of x. There are few exercises which will be translating the English sentence into logical expression. Say for example, I have every student in this class has studied calculus. So this will be for all x, s of x implies c of x. So here s of x is a student x. This indicates for every student, and c of x indicates the calculus. Some student in this class has visited Mexico. There exists x, s of x and m of x. Every student in this class has either visited Canada or Mexico. For all x, s of x implies c of x or m of x. So we'll be practicing this more, and gradually as we practice, we'll automatically be able to convert these English sentences into logic. Thank you.